Welcome to Lesson 21, Surface Area. And in this lesson we will be finding the surface areas of three-dimensional objects whose surface area is composed of triangles and quadrilaterals. Okay, surface area. We will use polyhedron nets to understand that. Okay, so understand that surface area is simply the sum of the area of the lateral faces and the area of the base, or sometimes bases. Okay, so we will be looking just to add, of course, sum the area of lateral faces. We'll talk a little bit about that coming up, and also the bases of a three-dimensional object or three-dimensional shape. Okay, for example, a refresher, a cube and its net, and I excuse me, call it a refresher because those of you who did the cube problem of the month, and I'm sure there's many of you out there, remember or might recall that you had to come up with the various nets that could be folded or constructed into a cube. And you can see right here, here's one of those. One of those nets was this one here. It's got kind of like a cross, and when folded up, makes a closed cube like this one here. Okay, so it's actually been able to go from 2D here, 2D, which is two-dimensional, okay, because that's what all nets are. They're two-dimensional. It can be transformed into a 3D or three-dimensional object. Okay, so when we are doing surface area, we will be calculating the two-dimensional aspect of these three-dimensional objects, okay, and that's the surface. We're actually just going to find out how many square units all of these faces and bases are actually worth. Okay, so poly means many, and hedron or edron, the last part, E-D-R-O-N, means face. Okay, so when you see these this term polyhedron, it just means a many-faced shape or object. Typically more than 6 when you're talking about a polyhedron. Okay, we're going to be looking at other shapes, other objects that are less than 6. They have other names, but polyhedrons will also come into play. We'll be able to look at those. Okay, and here are some polyhedrons that you may have seen. They all qualify as being a polyhedron, many-faced. You probably see the dodecahedron right here. That is I think 20-faced polyhedron. Okay, so yes, when you see that term used, just know that we are talking about shapes and objects such as these here. Okay, so here, if you just again notice, just going a little bit further with this idea of the nets. Okay, you can see here is a little worksheet. Match each of the following 3D shapes to the appropriate net. Okay, so let's start from the top, and we have the first one is a cube. Okay, and which one there do you think will turn into a cube? Guess is made. There we go. And there's our cube. Oh, geez. Oh, gosh. Sorry. Let's go back to that. Oh, no. No. Here we go. Okay. Okay. I should have done this one at a time when I produced it and put it together. But anyway, yeah, there's the cube, and you can see that net, and that might be again with the cube, counting cubes. problem of the month, the first one we did. You might have seen that. That net might have been familiar to you. Okay, and that, when that is all put together, goes from that 2D shape, or 2D net, you see, and can be folded into a 3D cube. The next one is what we call a square pyramid. Okay, let's slow this down. It's going too fast. A square pyramid, it's called a square pyramid, and we'll talk about these things more and more throughout, but it's called a square pyramid because its base, see its base right there, that is a square, okay? And when the sides are folded up, it looks like the pyramid that you see there to the left, okay? But it's called a square pyramid because of that, its base being square, okay? Next one is a rectangular prism, okay? And a rectangular prism, as you can see, anything that is three-dimensional, pretty much we can refer to as a prism, okay? A cube is simply a square prism, truly, but we call it a cube, has a special name. Rectangular prism is there, and you can see how its shape works. You can see all of its faces here are the longer sides, okay, and then you have these two would be your, actually wouldn't be your base, actually would be your side. They'd be faces. Actually, one of these would be a base, because one thing we'll learn later on, and we'll see again, is that any kind of prism, they are named according to their base. Okay, so a rectangular prism, you can see how it's lying there. Its base we consider to be the rectangular part. That's interesting. I mean, we could tip the thing over, you know, and it would still be a rectangular prism, but we wouldn't be sitting on its base. It would be sitting on a square. So, yeah, just a little touch, just something to know and for the future. So, next one here is a triangular pyramid. Okay, and there it is right there. Again, now similar in a sense to the square pyramid, except that, as you see, its base is a triangle. Okay, there's a triangle right there. That's its base. Fold up those sides, and it would be a triangular pyramid. Okay, and again, we're just here going from nets to the three-dimensional objects, okay, or vice versa. Okay, just trying to see how these things work. Next one we have is a cylinder. Okay, cylinder, very special in that we wouldn't necessarily be folding this part, we'd be rolling it up and then folding these two in. Okay, folding those two in. Those little round things along the edge of those, I'm just assuming are just little flaps if we wanted to glue them together, glue those to the longer cylindrical part. Okay, but yeah, this would be rolled up. That's a cylinder there. And last one, anybody want to give a guess as to what this one is called? Yes, it is a triangular prism. Okay, and you can see that. Oops, triangular prism. You can see we have again a prism, but it's got the rectangle as its base. All prisms have a rectangle as their base. Okay, and then if we fold this side, these sides up, and then those sides up, we would have that shape right over here. Okay, again, and we'll talk about this again later, but that word prism, if you see a rectangular prism, prism is going to have a rectangle as its base. All right, here, so surface area using faces and bases. Okay, so faces and bases. Just think of surface area as faces and bases. Again, taking two-dimensional measures. And that's what that word area tells us. Always two dimensions. So we're talking in square units. Okay, so there we see we have faces and bases. All right. Okay, so let's go ahead and now that we're through with that introduction type information, let's go ahead and go to our opening exercise. All right, this could take some time. The one thing most time consuming about this lesson is will be actually turning these three-dimensional objects you're going to be given, like this one we see here, up in the right-hand corner of my screen, upper right-hand corner, and then turning those into nets, okay, two-dimensional nets that will help us determine the area, or the surface area, okay? All right, so let me read this to you. It says, on the provided grid, draw a net representing the surfaces of the right rectangular prism. Assume each grid line represents 1 inch. Okay, we're talking in inches, as you can see, is also represented on that by that drawing. Okay. Then find the surface area of the prism by finding the area of the net. Okay, so what we're doing is we're going to take this three-dimensional object, okay, and we're going to flatten it by drawing its net, and then we will go ahead and be able to find its surface area that much easier, okay, that much easier. So what I'm going to do, I'm not going to let you go and do this. I want to do this, let's actually go ahead and do this together, okay? If you have an idea, and if you want to go ahead and give it a whirl, now there are more than one way to, there is more than one way to draw this net, but I have one in particular that I am fond of, a way to start, and I'll go ahead and show you that right now. It'd be nice, but again, if you want to try it yourself, go ahead and do it, and come on back. Okay, so first I'm going to go ahead and I look at my dimensions. If I took the three dimensions of this, it is 3 inches wide, okay? It is 4 inches deep and 6 inches high, okay? That's the way I'm looking at it, all right? So I need to know that. So what I can then do is I know with those dimensions, I also know other dimensions as well, okay? And I just filled those in there because I know that side, all the height lines of height are going to be 6 inches, the lines of width are going to be 3 inches, and the lines of depth are going to be 4 inches, okay? So flip the top open first. This is what I am doing, and I'm not telling you that you need to do this, but I like to be able to see it because I don't have a picture of this thing. I mean, if I created it out of paper, I could, and then I could help me out. But if I flip that top up, okay, I know that the top of it is going to be 3 inches wide. Okay, and that's what I've drawn that line there for 3 inches wide. Okay, and I know that it's going to be 4 inches deep, or 4 inches the other way, because I can see that up top here. Okay, there's my 4 inches right there. All right, so now I've drawn that top of it. I've flipped it open. Okay, and it's flipped open. All right, and what I'm drawing right there is a little dotted line. All those dotted lines are folds. Okay, are folds where one section actually meets another section. Okay, so you can imagine those would be folds of this box as I open it up. Okay, now I'm going to flip out the sides. Okay, I'm going to flip that out and flip out that right side, or yeah, we'll call it the right side as we look at it. Flip out that right side, and I know that it is 6 inches high. Okay, 6 inches high, and I also know that it's going to be 4 inches wide now. So let's go take a look at what that looks like. Okay, and there we go. All right, so what I've done is I've taken that side, flipped it out, and that's what it's going to look like right now. So I have, just imagine, again, imagining is a good thing, but it is a very challenging thing sometimes. Okay, so imagine just flipping that top up, and I got that one part, the 3x4 area, and then I flipped that one side out, I got a 4x6 area. I can do the same thing on the other side, okay, because you're always going to have this symmetry in three-dimensional shapes, especially such as rectangles and squares. Okay, so now I have looks like almost like two wings there. Okay, now you imagine again. Look at this box and imagine what I've done. I flipped the top up, flipped the two sides out, and you can imagine what you see. You see I got that front part that front flap is still there. You get the flap underneath, and you get the flap in the back. Okay. So next, let's go ahead and yeah, let's just let's draw that bottom. Okay, so that bottom right there, we can see is a 3x4 because it's going to be the same as the top. Okay, which is also 3x4. And that's that little part I'm pointing to with the arrow. Okay. Now you can see that the dotted section in the middle. That's the back of the of that box. As we look at it, it's the part, well, one of several parts we can't see. Okay. And now we have the final piece is that front flap. And if I flap that down, okay, it's this. As you can see, it is going to be 4x6, okay, because it's 6 inches high, and it is 4. Actually, no, it's not 4. It's actually, I kind of messed that up. I remember now. That's going to actually be 3, and I think I fixed it. So, area calculations. Okay, I'm pretty sure I fixed it, but let me go ahead and erase it now because I know I messed this up. This is actually going to be 3 there. Okay, that's 3 because that's going to be the same as that piece, this piece right here. Again, I know I'm going to color over this later, but this is a 6x3, and therefore this is the same size, 6x3. Okay, because that's the front, and then the one on the back. Okay, and I'm going to just take all of what I just did out. Okay, okay. So here's the area calculations. Now we have several areas to actually calculate. Okay, so those 2 green sections there, okay, and we got the 2 blue sections. It's probably, let me slow this down a little bit. Okay, let's just let me go back and we can just let's talk about this one at a time. Okay, all right, let's talk about these green areas. Now I'm working with them together because they are the same. Okay, they are the same, and later on this process will be spoken of again, and will be quite helpful. So the 2 green areas are 3x4. Okay, so I have 2 of those. So I have 2 on the outside of my parentheses. 2 times 3 times 4, which is 12, is 24. So those 2 represent 24 square inches of area, of surface area themselves. Okay. Now I have these blue wings. And there's 2 of those as well, and they are 4x6. Okay. Oops. Stop. They are 4 by, I don't like that. Okay, they are 4x6. Okay, and so therefore I have 2 times 4 times 6, which is 2 times 24, which they represent 48 square inches of surface area. Okay, now we get to my, there we go, to my purple. See, I took that out there. My purple pieces. Okay, and back. My purple pieces, all right, those are the 2 flap, that one larger flap we talked about, and the one same size in the back, the front and the back face. And you can see those 2 are 6x3, okay, 3x6 pieces. So we have 2 times 3 times 6, which is 2 times 18, which is 36 square inches of surface area. Okay, so you could see I have 1, 2, 3, 4, 5, 6 different faces and bases. Okay, and again, as this is a rectangular prism, it's made up of all rectangles, so truly doesn't matter which is your base. But in this situation, we look at our base being look at number 6. Number 1 and number 6 could be the bases, the way it's sitting. Okay, but anyway, they're all faces, truly. So bases and faces, all the bases and faces, there are 6 of them. Okay, and if I add all those up, I get 108 square inches of surface area. Okay, 108 inches squared of surface area. Okay, so again, we've taken this 3-dimensional object, we've imagined it in 2 dimensions by flipping it down. Again, if you went and tried this by yourself, your net might have looked different, but as long as it was able to be folded into a 3-dimensional rectangular prism, it's fine. Okay, so next, let's talk about the rectangular prism. Okay, Rectangular prism is a surface area formula for a rectangular prism is this. Okay, as it's drawn here. Kind of interesting to watch this happen without my having to do anything. Okay, because I've drawn all this stuff ahead of time, and I just push a button and it draws, and I can make it faster and slower. I'm sure you see what I mean already. But anyway, yeah, this rectangular prism, the rectangular prism, surface area formula for a rectangular prism is 2 times LW times L times W, which is length times width, plus 2 LH, which is length times height, plus 2 WH, which is width times height. Okay, and you can see here we have our 3 different dimensions. Okay, or actually these are different dimensions truly. Okay, length, width, and height. We know we're talking about a 3-dimensional shape, 3-dimensional object. Okay, but a rectangular prism has a formula, and there it is, and that's exactly what we did with our color-coded picture, which I should try to go back to right here. As you can see our 2, 2, 2, 2 3x4s, 2 4x6s, and then 2 3x6s. Okay, it's the same exact idea. And here it goes again. Sorry, I went backwards. Kind of hard to go backwards. So here we go. Surface area formula. Here it comes. All over again. Length, width, height. Alrighty, 3 dimensions. Okay. And there they are. Okay, so here are some rectangular prisms. Okay, and they are rectangular for a reason here. Actually, these are not rectangular prisms. Excuse me. Let me take that back. Okay, because we are about to talk about something else. We're actually about to talk about a right prism. Okay, these are all what are considered right prisms. Okay, and they are right prisms because they all have a right. They're made up of right angles at some place. Okay, 2 end faces, bases. Okay, that's what you can see there. So in this case right here, you have the 2 end faces or bases. In this one, they are triangular. You can see the triangle. Okay, in this one, they are pentagonal. And you can see the pentagon here, 5-sided shape. In here, they are square. Okay, 4 sides that are all equivalent sides, and then a rectangle, 4 sides which aren't necessarily equivalent. But of course, you know that a square is also officially a rectangle. Okay. Anyway, so 2 end faces, bases, which go along with their names. Okay, you have the one there and the one on top as well. Okay. Now prisms are named by their bases. Okay, and that's why. And here we go. I had done that before. I just did the new blue circling and such. But yeah, the prisms are named by their bases. So this right triangular prism has a triangle as a base. Pentagonal as a pentagon as a base, square, square, rectangle, rectangle. Okay? So important point or important note here is the rectangular prism formula 2LW plus 2LH plus 2WH does not work for all of these. Okay? Very, very important. Does not work for all of these because we have these different shapes that are going to be handled differently. Now, the only 2 that the 2LW plus 2LH plus 2WH are going to work for would be the square and the rectangular right prism, okay, because they are, both of them, rectangular, okay. The other one's a triangle, because we know right away that the area of a triangle is calculated differently than the area of a rectangle, okay, and a pentagon as well will be calculated differently. Okay, so with that in mind, I wanted to just give you a little refresher on this idea of right prisms, because we have a right prism in this next activity, this exercise 1. Okay, and let me go ahead and read this to you. So Marcus thinks that the surface area of the right triangular prism will be half that of the right rectangular prism, and wants to use the modified formula SA. He's saying the surface area. SA stands for surface area of this right triangular prism equals 1/2 2LW plus 2LH plus 2WH. Do you agree or disagree with Marcus? Use nets of the prisms to support your argument. And again, this is one I would much rather you do along with me, pausing as you go as I move through solving this problem. Again, pause because I might go a little bit too quickly, but what Marcus is trying to do, and let's see what I first did. So, the rectangular prism first. Okay, so let's go ahead and handle that rectangular prism first. Okay, and we know our rectangular prism formula is going to be 2LW plus 2LH plus 2WH. Okay, and I'm not sure if I've drawn this before, but let me do it again anyway. But the rectangular prism we are solving for right now is all of this here. Okay, is the whole entire shape. Okay, so we're trying to figure out the surface area, okay, of this entire larger shape. Okay, so I'm going to go ahead and just take those off. Okay, all right. So we have and 2, and this is actually the same exact calculations as we did before. Okay, and you're going to see we're going to come up with again 108 square inches, because that's the exact same rectangular prism that we were working with before. Okay, and we got our 3x4 portion. Okay, which was right here. Those are the 2 bases. Okay, we had our 4x6 pieces, which were these lateral faces here, and then we had our 3x6 faces, which were right there, front and back in this case. Okay? All right, so we're going to test this idea of the surface area of the triangular prism, and you can see that triangular prism as it is drawn in here. But let's go ahead and write down what Marcus said. Now, Marcus is thinking if his if his formula is correct, this rectangular prism, when we calculate its surface area, will come up to 54 inches squared. So Marcus, give him credit. He's trying to come up with a shortcut. Okay, shortcuts are always well appreciated in math, but they don't always work. Okay, so we're going to go ahead and test his theory here, or his modified formula right now. Okay, so the triangular prism. Okay, let's go ahead and look at its formula, and let's look at what we're talking about. Okay, so we are talking about this this piece that goes right here, and again, I don't know how much of this I drew, but all of this right here. Okay, so that on the outside, but just cut in half, and here's the line where we're cutting it in half, right there, right across this line. Now you can see this line is actually 5 inches long. Okay, first of all, it's going to throw off our calculations if we're thinking about it. It's going to throw off our calculations quite a bit, because we had no 5s to deal with when we were figuring out the rectangular prism first. Okay, all right, so let me just get rid of those blue strokes. Okay. All right, so what we're doing right now is we just drew that 6x5 base portion. Okay, and that was this right here. If I'm going to go ahead and draw that, and again I have this here. Okay, I've just drawn the bottom, that base right here. That if I flip this over or flipped it sideways, just if I cut it in half and then set it on its square base, I could do that. It would be the 5x6 portion. Okay, so that's that right there. Okay, and again, let me get rid of these blue strokes, as I'm sure I've drawn something similar already. Okay, and there's my fold. Alright, take all that out. Okay, just erasing that, and again you can probably see even in the gray, you can see that that is the, not necessarily a base, it's actually one of the faces, okay, because truly this is, if we're going to call this, and it is a rectangular prism, these, the bases of course, so prisms are always named after their bases, so they would be thinking of these being the bases here. So here's the top base, and here's the bottom base, which it is sitting on. This over here, that gray, is actually a side itself. Okay. All right, and here we go. Okay, so now we're looking at that part. Okay, we're looking at that lateral face. Okay, we've got the larger lateral face, which is that gray face. And now you can see if we've folded this thing out, folded this down that way, okay, you'd see that this would be sitting, or folded the whole thing out that way. This would be, actually, now let me take that back. I don't like that, because actually we would have folded the back base out that way, and then this one would have been there. So here's this dotted line I just drew there is actually right here. That's that dotted line. Okay. Okay. All right, so that's a 3x6 piece, and you can see that right here. This is 6, and this is the 3, and here would be the 6, and there's the 3. Okay? All right, let's go ahead and draw that one. And that you can see is 6x4. You can see that. I've got the 6 here and the 4 here. All right. So now I have the 3 lateral faces drawn. Okay, the 3 lateral faces. That back, the gray one, the gray part, this part up front, this one here, and then this face here. Okay, those 3 lateral faces I have actually turned into 2-dimensional representations or nets down there. Okay, get rid of these strokes. Okay, all right, let's go ahead and clean that up. So now I'm looking at my 2 bases. Okay, I have two bases, and again, these are my bases because this is a rectangular prism. I'm sorry, it's not a rectangular prism, it is a triangular prism. Okay, right here, and we know that prisms are named after their bases. Okay, so here are my bases, those 2 triangles. Okay, and those triangles, then, if I folded all, just imagine I folded all those lateral faces out, these bases, this one here, and this one here, okay, would fold out to the side and look like these 2 here. Okay? Oh, let me just, wait a minute. Oh, shoot. Get rid of all that. Okay, so I'll get rid of my blue strokes. All right, so now I have those 2 bases, okay, and those 2 bases are triangles, okay, and my triangular formula for area, okay, is 1/2 base times height. You can see that right here. This is what we learned. We learned before a few lessons ago. Okay, so we can actually do that. We can figure out the area of those 2 triangles. Okay, and those happen to be right triangles, as you can see, by the fact that they are right angles right there. Okay. All right, and then we can go ahead and look at the one larger rectangle. That's our largest rectangle, and very simply, the area formula of a rectangle is length times width, or base times height, however you want to look at it. That's very simple. 6 multiplied by 5, and that's 30 square inches. Our next rectangle is 6x4, 24 square inches, and our final rectangle is 6x3, and that's 18 square inches. Okay, so there we have done. We've figured out the area, the surface area of all of these 2-dimensional shapes now that sit as a net. Okay, so if we go ahead and then add all of those different areas up, we get 84 square inches. Okay, and what we're adding up, we are adding, so now we know it does not work. But again, we got that 84 inches. we added our 30 square inches plus 18 square inches plus 6 square inches plus 6 square inches plus 24 square inches, all 5 of those faces and bases, and we came up with 84 square inches. So this this triangular prism that was created by cutting that rectangular prism in half, okay, is actually a lot more, is a lot greater, actually 30 square inches greater than this improvised formula, this shortcut that Marcus was proposing, okay? So yeah, it does not work as a shortcut. And again, the reason is we're talking different shapes now. We're talking triangles and rectangles in the same three-dimensional shape. Okay, so here we are again, back at our right prisms. Okay, one very important commonality among right prisms. Okay, and let's see if you can guess what they are. What the one very important commonality among right prisms, and that is that right there. And what do you think that shows us? What that shows us is that rectangular lateral faces. Okay, all right prisms are going to contain rectangular lateral faces. So all of their lateral faces are rectangles. Okay, all of them. The only thing that changes, of course, are the bases, and we talked about right prisms being named by their base. Okay, so right triangular prisms are going to have all rectangular lateral faces, but it's going to have a triangular base. Okay, triangular bases. Okay, it has two bases, one on top, one on bottom. Right pentagonal, same idea, all rectangles. Okay, as lateral faces, but the two bases are pentagons and square, and of course rectangular, of course. Okay, so here we go. Let's talk. I hope we're going to use some of the vocabulary I just spewed out there. This idea of lateral area of right prism. Okay, so this example 1 here, it says a right triangular prism, a right rectangular prism, and a right pentagonal prism are pictured below. And they all have equal heights of h. So as you see now, we are not using a number value. Look at that. We're not using a number value for our dimensions, but we are actually using letters and or variables. Okay, which we are, of course, it's we're all about algebra, and we need to get to our variables at some point or another. Okay, so all of them have equal heights of h. So you're going to use that information, or we are going to use that information to answer some questions. And actually, the first one's going to ask us to write an expression, and we really are back to algebra. Okay, so what we're going to do here now is I'll just read this question to you, and then I'd like for you to try to pause and try it yourself, and come on back if you're having difficulty, or come on back just to do it along with me. Okay, so A here says write an expression. Okay, write an expression that represents the lateral area of the right triangular prism. Okay, we're just talking about the right triangular prism first, as the sum of the areas of its lateral faces. Okay, and again, remember that these are the lateral faces, are right here. Okay, this one, there's going to be one on the other side, another lateral face, there's going to be another lateral face on the other side. Okay, these here, of course, are the bases, this one here, and that one that sits at the bottom there. Okay, again, looking at things three-dimensionally, on a two-dimensional surface like this piece of paper, or this screen that we're all looking at it now, is very difficult. Okay, but again, we're going to want you to write an expression that represents, okay, you know what an expression is, it's not an equation, it's just an expression, okay, what plus what plus what, all right? That represents the lateral area of the right triangular prism as the sum, okay, and that'll tell you it's plus, right, of the areas of its lateral faces. So go ahead and give that a whirl. It may sound like gobbledygook to you, and I wouldn't be surprised. But go ahead and give it a whirl. Come on back, and we'll do it together. Okay, so here we go. Let's write this together. Hopefully you have it already. Let's write an expression here that represents the lateral area of this right triangular prism as a sum of its lateral faces. So first we have HC, which is H times C, okay, and that would be right here. H is the height, and then C as the length, okay, and that is the height times the length. H times C. That's going to give us this lateral face, okay, area. All right. Next is we're going to add then HA again, which is this one right back here, that face that sits in the back that we really can't see. All right, and that's going to give us the area, the surface area of that lateral face. And then the last lateral face is H times B, which is that, here's B, which is that back area there, that back lateral face that we also cannot see. Okay, so there it is. That's our expression. Again, we need no equal sign, okay, because we didn't ask for any equation, okay, but you could use this in an equation, of course, in the future. But there it is. There's our expression. That's how we would get the sum of all the areas of all the lateral faces would be that expression. Okay? All right. Let's go ahead and move on. Here we go. I've just brought these back so we can actually see these. And now B here asks us to write an expression, again, that represents the lateral area of the right rectangular prism. Okay, so we're on the rectangular prism, which is the one in the middle, as the sum of its areas of its lateral faces. So we're actually doing exactly what we did with the right triangular prism. Okay, so go ahead and do that now that you have some experience with that, and come on back. Okay, now this one was kind of interesting, and hopefully you saw something or some way to actually simplify this expression. Okay, so I started off with HA, which is H times A, which is right here. Okay, and that would be that lateral face that I would be calculating there, that area. And then HB, okay, which is right here, because this is H over here, of course, HB, and that's the area of surface area of that part, okay, and plus another HA, which is happens to be that back lateral face, okay, and then another HB, which is going to be that lateral face over here. You can actually see through there, see right through there. That'd be that one. Okay, and then we have a BA, okay, which is down there. That's one of our bases, okay, right there. That's the area of there, surface area there, and another BA, okay, which is the top base right there. Okay, so now you might notice that we have some repeats here. A couple of HAs, a couple of HBs, a couple of BAs. Okay, so you could also express this as 2HA plus 2HB plus 2BA. Okay, so and it's kind of what we've done here in terms of algebra is we've actually combined like terms. Okay, we've combined like terms by putting all of those together. Okay, so now C asks us to write an expression that represents the lateral area of the right pentagonal prism as the sum of the areas of its lateral faces. Okay, so again, doing the exact same thing we've done for the right triangular prism and the right rectangular prism. Just go ahead and see if you start seeing some something that looks vaguely familiar to A and B as you do C. Okay, so go ahead and come back and we'll look at it together. Okay, so here we go. First we have AH. Okay, again, H is real popular here. AH, and again, that's that lateral face. Okay, and then we have BH, which would be right here. CH, like you're getting that's that one back there. And again, we're just talking lateral faces like we have the whole time. BA is CH, and then we have DH, which is right there. Okay, and EH, which is this last one right here. Okay, so all those lateral faces would be summed up this way. Okay, so D asks us a very, very curious question, and hopefully you've been noticing what value appears often in each expression and why. Okay, why? Which value? And again, there's no number value here, but we're going to look at a letter. Which letter value appears often in each expression and why? And if you notice, I don't have the first triangular right prism, but you can see here's H, 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 H. Okay, and then we have H, 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 H. Yes, and that's indeed it is H. H comes up very often, and why is that? Why is that? Well, the reason it is because first of all we said that each prism has a height of h. Okay, so they're all equivalent in that. Okay, so each lateral face, if the prism itself has a height of h, each lateral face is going to have a height of h. Okay, so h is going to be very, very prominent, or this height factor is going to be very, very, very prominent in calculations. Okay. Okay, so letter E asks us now to rewrite each expression that we just wrote for all three of those prisms. Rewrite each expression in factored form. Okay, factored form. Factored form actually came up on the mid-module assessment for 3, and I think some of you might have been a bit confused by it, but we'll talk about it now, and hopefully you can come more clear. Using factored form, using the distributed property and the height of each lateral face. Okay, distributed property is going to tell you some things, how it's going to look. Thinking distributed property, you're always thinking of parentheses. Okay, and then you're going to use the height of each lateral face. Therefore, we might be able to safely assume that that might be how we are going to factor. Okay, so let's go ahead. I'm going to go ahead and get these expressions here. This was the expression for the triangular prism. Okay, the triangular right prism, a right triangular prism. Here's the right. That was the right. Oh, here we go. Right rectangular prism, and then here was the right pentagonal prism. Okay, and those are the expressions we came up with. All right, so now your job is to go ahead and write each of those in factored form. Okay, and if you can use some of the hints I just gave you, come on back and we'll see how you did. Okay, so let's go ahead and look at these one at a time, starting with our right triangular prism, which is the HA plus HB plus HC. Now, if we find a factor, okay, when we factor these out, we're trying to find the largest factor that is common to all of our expressions here. Okay, and we can see that that is H, because H appears in all of those expressions. HA, HB, and HC, they all have an H in them. Okay, so my parentheses are going to go there. Now, inside those parentheses, I am going to put the terms I need in there that would, when I distribute them out, would equal HA plus HB plus HC. And those, of course, are A plus B plus C. Okay, so if I go ahead and distribute, and I'm not going to do this with with all of them, but I will do it with this one here. But Remember when we distribute, H times A, that's our HA. H times B, that's our HB. H times C, that's our HC. So here, this second expression here is factored form. Well, we've actually removed one of the common factors from all those three expressions and put it outside the parentheses, and then then put the other terms inside of the parentheses. Okay, so let's go ahead and take a look at our next one. And again, our factor, our greatest common factor in that sense, is H. It appears in each expression. Okay, and there we go. We have H times A plus B plus A plus B. Now, I went ahead and took it a little bit further, and I saw that actually there were two HAs and two HBs in that expression. So I went ahead and used 2H as my factor, and then A plus B in there. And that would probably be what we consider simplest terms. Okay. For our last one, for the pentagonal, right pentagonal prism, we had, of course, H was our factor. Again, the greatest factor that was common to every expression. And, of course, A plus B plus C plus D plus E. Okay? Because if I did my distributive property, this right here would turn into this right here. Okay? So, again, this is factored form. The ones in the red, those are in factored form. And this next question, question F, is really, really incredible and so interesting when you actually do see what it does represent. And it asks you right here, what do the parentheses, or actually the values in the parentheses, in each case represent with respect to the right prism? So what do these three values here what do they represent in the case of the right triangular prism, whereas these would be the right rectangular prism, and these would refer to the right pentagonal prism. So I want you to think about that. Go back to your to the drawings, to the work you've done in the binder, and take a look and ponder that, and come on back and tell me. So, what do they, all the parenthetical portion, what does that in each case represent with respect to the right prisms? Really, really quite fascinating. And come on back, see if you get the right answer. Okay, so I wonder who got it, who came up with the answer. Really, really, I think quite fascinating. So, yes, what do the parentheses in each case represent with respect to the right prism? And again, the values in those parentheses. Okay, here's I'm going to put it out there one at a time. If you didn't get it, or if you did think you got it and you notice that you're right, you can do Yippee Yahoo at any given time. But if you didn't get it right, let me give you some hints with these letters. So first letter is P. Some of you might be Yippee Yahooing right now already. E. R. I. Peri. What's peri mean? Peri means around. Okay, peri. Yeah. Perimeter. That's right. The perimeter of the corresponding prism. Really, really cool. I spelled prism wrong. Anyway, let me get... Oh, man. Sorry. Bothers me. Prism. Yes, the corresponding prism is the perimeter of the corresponding prism. So let's go ahead and go back and look at that. Okay, so if we look right here, let's go ahead and look at the triangular, the right triangular prism, because it's the one that I haven't messed up yet. If you see it there it is. It is A. There's A. There's B. And there's C. Okay, if you go back to ours, you can see there it is. A, B, A plus B plus C. If you go back to let me clean this thing up here. Go back to the rectangular prism, right rectangular prism. Here we go. We got A plus B plus A plus B. And there it is. A plus B plus A plus B. Okay? Or 2A plus B. All right, and then we go to our, finally go to our right pentagonal prism. And here we see, we've got A, so A, B, C, D, E, and there it is, A plus B plus C plus D plus E. Very, very interesting. So now what this does is it leads to us being able to generalize. So let's go ahead and look at this G here. G asks us, how can we generalize the lateral area of a right prism into a formula that applies to all right prisms? So again, we are always trying to find some level of shortcutting in math, okay, which is okay, all right, but we are trying to generalize the lateral area of a right prism, okay, and this is all the lateral faces only, okay, into a formula that applies to all right prisms. So it has to be able to apply to all right prisms, and the prisms we're talking about here are pretty different. You know, you have a triangle, and then you have a rectangle, and you have a pentagon. Okay, so go ahead and see what you can come up with, and again, it's going to be an equation. Okay, something equals something. Well, I'll give you a hint. Something times something. Okay, so give that a whirl and come on back. Okay, so we're going to generalize the lateral area of a right prism, and again, any right prism. A formula we might create might look like this. Okay, LA equals, and again, LA standing for lateral area, and again, I'm not sure how formal or official this is, but for our sake, we are going to use that. So the lateral area of any right prism would equal P, and that's the perimeter, and the perimeter of the base. Okay, and that's how that would be written, kind of a subscript base. So P means perimeter of the base. What do you think's next? It's going to be times what? Yes, I'm sure you know. Times the height, okay? Because we have this familiar height value that seems to be around all the time because, well, we know it is because every lateral face includes the height, okay? Includes that height, which is always going to remain the same. And the perimeter, as we found out, the parentheses, that parenthetical, and you can see it right here, right in front of us. If we just take a look at what we have here, you can see this this formula playing out in all of this right here. Here you go. Here's the perimeter of the base would be this right here times the height. That's right there. Perimeter of the base, which is here, times the height. Perimeter of the base times the height. Okay, and yeah, so there you have it. All right, let's go ahead and close our lesson now. And this is a long one, a lot of new stuff, a lot of maybe challenging stuff, but hopefully satisfying and fun at the same time. Okay, so this relevant vocabulary page, lots of words on here. You know, the way they're described sometimes can be in somewhat confusing language. I'm not going to go over it, but I'd like you to. These are things that I've talked about throughout this lesson already. This idea of the right prism. We talked pretty much at length about those and the different parts of them. We have base faces, and then we have lateral faces. Okay. We talked about cube. Many of us know a cube. It's just a right rectangular prism whose all edges are of equal length. And surface, the surface of a prism is the union of all of its faces. So when we added all those face areas together, we come up with the surface, or the surface area. Okay, and a net is a two-dimensional diagram of the surface of a prism. Okay, so it's a prism or a three-dimensional object that is flattened out, all its pieces, and then measured. Measured to get the surface area, of course, but the net itself is just the flattening out of all of those faces. Okay? Okay, so a couple of, last 3 points before a little lesson summary. Again, some of this is more valuable than than other. Doing this type of activity is the best way to become fluent with this material. So the first question is, why are the lateral faces of right prisms always rectangular regions? Well, if you think about it, if you have a see if I can actually make this here. I'm trying to make a right triangular prism. Okay, oh wait, hold on a second. Don't like that one. Okay, there we go. So then we're going to have it like that, and then like that. Okay, kind of like that, alright? That's kind of messy, but I am really very artistic, believe it or not. I think some of you know that already because you had me in art class as a teacher, which I really loved and really miss. Yeah, so there we go. We have a right triangular prism, or so we think. Anyway, the reason the lateral faces, so all of these faces here, I've got the lawnmower in the background, please excuse that noise. All of these lateral faces, the reason they are all rectangles is that where the bases meet, or the lines or the line segments that create the bases, they meet at it's a perpendicular point where they meet the height. Okay, the lines of height. Okay, and you can see right there, these are all perpendicular, which means they are 90 degrees. Okay, and because they are 90 degrees, all of these here, they're 90 degrees. They're all going to be rectangles. Okay, and that's the case of the rectangular prism, of course, pentagonal prism, hexagonal prism, right prism. Okay, and again, that idea of being a right prism means it's going to make a series of right angles. Okay, where the base lines, base segments, intersect with the height segments, or these side segments here. Okay, so that's why they're all rectangles. All right, and then it says, what is the name of the right prism whose bases are rectangles? Well, of course, it is a right rectangular prism. Okay, a right rectangular prism, because, as we mentioned before, all of our right prisms are named after their bases. Okay, so the bases lend the right prisms their names. Okay. Alright, so how does this definition of right prism include the interior of the prism? I do not exactly know what they're talking about, so I'm going to just cross that out for now. Okay, here we go. Here's our lesson summary. We are over an hour. So sorry, but had to happen. So here we go. The surface area of a right prism can be obtained by adding the areas of the lateral faces to the area of the bases. Okay, so two separate parts. You know, the lateral areas of the lateral faces, and which are always going to be pretty easy. They're going to be rectangles, so it's height times width or whatever. And then the areas of the bases, and they could be very easy. They could be rectangles or squares, but they could also be triangles or hexagons. Okay. The formula for surface area of a right prism, talked about that, is SA, surface area, equals excuse me, lateral area plus 2b, so LA plus 2b, lateral area plus 2 of the bases, where SA represents the surface area of the prism, LA represents the area of the lateral faces, and B represents the area of one base. Okay, and we have two bases. All right. The lateral area, LA, can be obtained by multiplying the perimeter of the base of the prism times the height of the prism, and that's one of the last things we did in this lesson. So, with no further ado, I will bid you farewell and wish you well on your problem sets and exit tickets. All of this that we just read here was pretty much covered in this lesson, so hopefully I didn't go too quickly. If I did, just go back and listen to me again, which I know is going to be a horrible thought for some of you. Anyway, yes, see you soon.